So we define this idea of concavity of a function, and these inflection points for helping us find that concavity. But what can we really use concavity for? Well, one application is another technique for identifying what the relative extrema of a function are. In the last section, we had that first derivative test to identify whether or not a particular critical point of a function was actually a relative maximum or relative minimum, or neither. Here we're actually going to do kind of the same thing, but using the second derivative instead. And the idea comes from what our pictures for concave up and concave down were. So for concave up, I've been saying that our graphs there kind of look like an x squared, where we have a kind of a cup shape to it. Here, if we actually have a critical point, say here at our minimum, it's actually going to be a low point because of the shape of the curve that we have. For concave down, I was telling you we have a cap shape to it. And here, if we have a critical point, a place where the derivative is equal to 0, it's going to have to be a high point. And that's the idea that we want to turn into a test. Basically, we're going to have what we call the second derivative test. Because we're going to be using the second derivative. We're going to have a function where f prime of c equals 0. Now, the first derivative test works when the first derivative at c doesn't exist. We can't actually use the second derivative test for that. We actually need the second derivative to exist not only at c, but around c. So the second derivative test right off the bat is a little bit more restrictive. We're only going to be looking at critical points where the derivative actually does equal 0. It has to exist, and the second derivative also has to exist. If both of those are true, which they are in a lot of cases, say any polynomial, that's always going to be true. If the second derivative at c is positive, well, remember that means that we are dealing with a concave up function. Concave up, we actually had a minimum. You might think, well, if it's positive, we have a maximum. No, it's actually, in the case where the second derivative is positive, we actually have a minimum. We have a relative minimum at c. If the second derivative is negative, then we're in this concave down situation where we have a cap. Now any critical point is going to have to be a relative maximum. Unfortunately, we also have the case where the second derivative is equal to 0. Unfortunately, here the test fails. And it actually really does fail there. In a case where the second derivative is equal to 0, it could have a maximum there, it could have a minimum there, or it just have neither one. In fact, if we have a critical point where the first derivative is equal to 0 and the second derivative actually exists and it's not either a relative minimum or relative maximum, then the second derivative also has to be 0 there as well. In that particular case, we're going to have to fall back on this first derivative test. The first derivative test is definitely the more robust one because it applies in more situations than the second derivative test does. But the second derivative test doesn't actually require me to take test points. It only makes me test one function at one point. If I know f prime of c is equal to 0, I only have to test the second derivative at c. Now, there's not really a lot more to say about the second derivative test. We're just going to go right into working out some problems. We're going to start with problem 26. We have a function, f of x is equal to x plus 4 over x. They want us to find all relative extrema of this function and use the second derivative test to actually identify them. Now, I'm also going to go ahead and do what we were doing in the previous video. Let's actually identify the concavity and inflection points of this particular problem, just because it's going to illustrate a few points that I couldn't really make when they only gave me polynomials to work with. First things first, the domain of this is not all real numbers. When we had polynomials before, all of our domains were everything. So we didn't really even have to use the domain in those problems. The domain here can't include 0. We can't plug 0 into 4 over x. So it's all x, where x is not 0. Of course, we are going to be talking about the second derivative. We need the second derivative. In fact, we're also going to need the first derivative because we're going to be talking about extrema. So in order to take the derivative of this thing, first I'm going to turn 4 over x into 4 times x to the negative 1 power. That's going to be a little easier to work with. The first derivative of this function, well, of course, the derivative of x is 1. Derivative here, remember, we're using our power rule, so we're going to take that negative 1, bring it out in front. So instead of a plus 4, I'm going to have a minus 4. And then negative 1 minus another 1 is actually a negative 2. We can also write this as 1 minus 4 over x squared, because that's what the negative in the negative 2 power means. But I'm actually going to use this first formula in order to take the second derivative. Second derivative, this time the 1 actually goes away. So we don't have this first term anymore. We're going to have the negative 4, but then we're going to bring down a negative 2 as well. Negative 4 times negative 2 is actually a positive 8. And then our power goes from negative 2 to being negative 3. In other words, our second derivative is 8 over x cubed, if we want to write it that way. Now, one thing we'll note right now, if we want to determine where what the concavity of the function is and where the inflection points might be, this the second derivative, where we have a cube on the bottom, is never actually 0. Because, well, we never have 0 on the top. 8 divided by any number is never 0. So we don't get any possible inflection points from setting the second derivative equal to 0. Now, what about where the second derivative doesn't exist? We actually have to worry about that this time because we're not dealing with a polynomial. Where does this expression here not exist? Well, obviously it doesn't exist at 0. Unfortunately, 0 is not in the domain. So actually, we don't get any new points from this not existing either. We have one number line. We do have to include 0, not because it's actually going to turn into an inflection point, because it's a point that's not in the domain. We still have to worry about points not in the domain of the function. We can go ahead and pick points on either side of 0. Probably just pick negative 1 and 1. We're going to plug those into f double prime. Well, if you plug in 1, that's really easy. We just say 8 over 1, or just 8. You have positive numbers over here. With negative 1, we have to remember that negative 1 cubed is still a negative 1, so we get a negative 8. Basically here, our original function here, is concave up from 0 to infinity, and concave down from negative infinity to 0. And I'm gesturing wrong. It's concave up from 0 to infinity and concave down from negative infinity to 0. Now, f does actually change from being concave down to concave up, but that does not mean there's an inflection point at 0. There actually is no point there because there's literally not a point on the graph. Remember, the inflection points have to be points on the graph of the function. In fact, if we were going to go ahead and plot this thing, remember our function was x plus 4 over x, and we get this particular graph here. We're definitely concave down. It doesn't really look too much like a parabola anymore, but it still has the same idea of opening downwards. Then up here is concave up. It's opening upwards. There's no point in the graph at 0 because we have an asymptote there. Now, we can already tell from our graph here that we're going to, it looks like we should have a relative maximum here and a relative minimum here. Let's actually go ahead and do the math to find those, though, rather than use those ideas. So, again, we're going to go ahead and, well, basically all those stuff that we've been doing here was not in the directions. Now we're going to be identifying the relative extrema of the function. And we do that by taking our first derivative. We're going to set our first derivative equal to 0. So just going to set this equal to 0. Of course, that means that, so 1 equals 4 over x squared. We bring the x squared over to the other side. And when we take the square root, remember we need to do plus or minus. Now, at this point, we could do put a number line where we use that first derivative test and take test points, but we don't need to do that because we already know what the second derivative actually is. We have critical points at 2 and negative 2, and we know that at negative 2, since we are in this interval here, the second derivative is negative. And the second derivative is positive over here, where 2 is. We don't even have to work out what those are. Second derivative at negative 2 is negative. And the second derivative at 2 is positive. From our second derivative test, remember a negative second derivative at a point where the derivative equals 0 means that this point is a point where there is a relative maximum. So at negative 2, we have a relative maximum of the function. At 2, because the derivative is 0 and the second derivative is positive, we have a relative minimum. And that lines up exactly what we expected from our particular graph. At negative 2, so we've identified what the x value actually was at this maximum point here. But it is a relative maximum. So if negative 2, comma, whatever f of negative 2 is, which I guess is negative 4. But then at 2, and 2 comma 4, we have a relative minimum. We've identified those pieces of information about our particular function. Let's look at a problem where we don't look at the graph first before we do that part of the problem. Let's look at problem 24, where we have a function f of x, which is x cubed minus 5x squared plus 7x. Of course, I'll go ahead and identify what the domain of this function is. Since it's a polynomial, it's just all real numbers anyways, but I'm going to keep writing it there anyways. All we're trying to do in this particular problem is determine where are the relative extrema of this function and what are they? Are they relative maximums, relative minimums? But we're going to be using the second derivative test to find that. Since we're going to be using the second derivative test, we're going to have to differentiate this twice. Our first derivative, x cubed becomes 3x squared. X squared becomes 2x, but combined with that 5, we have a minus 10x. And then 7x becomes a 7. Our second derivative, if we differentiate again, 3x squared becomes a 6x. Minus 10x becomes a negative 10. And then the 7 goes away. But we're actually going to be using the first derivative first because we need to know where that actually equals 0. Or, well, where it equals 0 or doesn't exist. Of course, where it doesn't exist is not going to really matter for the second derivative test. because we actually need the to equal 0 for the second derivative test. This is a polynomial though, so we don't have to worry about that part. So I'm going to take my first derivative. I'm going to set it equal to 0. I'm going to have to factor this thing. Well, I'm going to have to hope that I can factor it. Otherwise, I'm going to have to use the quadratic formula. It turns out in this particular case it does actually factor. But which factors we have is maybe not completely straightforward. I do know that whatever I have from my first terms have to multiply to be 3x squared. That means we're going to have an x in both of them, but one of them is going to have a 3, and one of them is going to have to be a 1. At least, as long as it's not -1 and -3. But I can go ahead and pick positives for this first term. So I'm going to say we have a 1 here, and I'm going to have a 3 here. The other terms are going to have to multiply to be 7, which is probably going to be 1 and 7 or -1 and 7, -1 and -7. But I'm going to have to figure out which combination makes a -10 when I were to expand that out. Turns out the best way to do it is put the -7 here and the -1 here, because that means we have a -7x from doing the outer ones and a -3x for doing the inner ones. And when you add -7 and -3, we get a -10. But that one's not as straightforward as maybe some factorings is. Point here is, though, when this equals 0, x is either equal to 1 or x is equal to 7/3. Those are our two possibilities. And we don't need to make a number line because we're using the second derivative test. We actually are looking at what is the second derivative at these two particular numbers. What is the second derivative at 1? Well, there we have 6 minus 10, which is a -4. The fact that this is a negative at 1 means that we have a relative maximum. Remember, when we have negatives for the second derivative test, it's actually a maximum, not a minimum. Might feel backwards, but that's the way it goes. Second derivative at 7/3. I'm going to have to put that in here. Actually, 7/3 times 6. We have 3's that can cancel out, leaving 7 times 2. We get a 14 minus 10. And we get a +4 this time. And a positive number for our second derivative means that we have relative minimum. Of course, we're going to go ahead and actually look at the graph of this just to get an idea of what this looks like. Remember, our function was x squared minus 5x, x cubed minus 5x squared plus 7x. We have this graph here. If we go ahead and put in our critical points, we had 1 comma at whatever the y value is at 1, which turns out to be 3. And then we have 7/3, comma whatever our y value there is, which is a less nice 1.81. But we had those two particular points. At 1, we definitely have a relative maximum. That's what we found before. And at 7/3, we definitely have a relative minimum. Again, agreeing with what we found. Let's go ahead and do one more problem of this. It's going to be a little bit lengthier than some of the other problems that we've done in this section. We're going to look at problem 48. We have a function g of x. This is equal to x times the square root of 9 minus x. And we're going to ask the same question of, well, first we need to find all relative extrema, and they actually do want us to find the points of inflection as well. So we're actually going to combine the previous two types of problems. But we want to identify any of these significant points about this graph. Of course, the first thing I'm going to do is identify what my domain is. This function does not have domain all real numbers. In fact, we need to make sure that we have no negative numbers under the square root. Now, you might think, well, from 9 onwards, but actually because we're taking 9 minus x, we have to look at the other side. Our domain is actually going to be from negative infinity to 9. And we can actually include 9 there. At 9, this just becomes 0. But we're going to have to differentiate this thing, which is going to involve the product rule, and we're going to have to use the chain rule for the square root part. And I'm also even going to go ahead and change this to 9 minus x to the 1/2 power. That'll help me out a little bit. So first derivative. Take the derivative of the first factor. Derivative of x is just 1 times the second factor as it already is. Now I'm going to leave the x alone, but now I'm going to differentiate the 9 minus x to the 1/2 power. Of course, using the chain rule here, I'm going to have to first bring down that 1/2. I'm going to leave the inside as it is for the moment, and then the 1/2 here we have to subtract 1 from that to get a negative 1/2. But we're not done yet because we also need to multiply by the derivative of the inside. Derivative of 9 minus x is actually a negative 1. So we have to multiply by negative 1. I'm actually going to simplify this a little bit. It'll actually help out a little bit. So first of all, I'm going to turn this back into a square root. Here, I'm going to bring that negative 1 and just change the plus sign to a minus sign. I'm going to use the fact that the negative here means that we are on the bottom, and the 1/2 is the square root again, and the 2 is already on the bottom. So I'll have an x on top, and a 2 times the square root of 9 minus x on the bottom. Now that may not look quite simpler, but what we can do here is we can actually combine two functions, or combine two fractions here. First thing I'm going to do is move that over a little bit, and I'm going to go ahead and put in here a 2 times the square root of 9 minus x over 2 times the square root of 9 minus x. Essentially, I'm making a common denominator here. On the bottoms of both these are going to be a 2 times the square root of 9 minus x. And so my result here is going to have that on the bottom, but I'm going to have to figure out what's going to be on the top. Well, first things first, this square root actually combines with that square root. This is actually 2 times 9 minus x, without any square roots anymore. And here we just have a minus x. So already it looks a little bit nicer than what we already had. But we can even go a little bit further and combine, well, this if we distribute the 2, we have an 18 minus 2x, but then we also have a minus x here. So we have an 18 minus 3 x's. And that's what I'm going to use for my derivative. Before we actually make use of that derivative, though, I'm going to go ahead and take the second derivative. You can probably see why I said that this is going to be a longer problem. There's quite a bit of differentiation going on here. And we are going to have to make use of the quotient rule here. When I take the second derivative, I take the derivative of the top. That part's pretty easy. We have a negative 3 times the bottom as it already is, so we have a 2 times the square root of 9 minus x. Then we subtract the top as it already is times the derivative of the bottom. Well, first of all, we already have that 2, and we already know how to take the derivative of 9 minus x from back here. So basically this second term that we have here, just without the x. The x was from the other factor. Everything else was from our derivative. So we're going to have the 2 that was already there. We're going to have a 1/2. We're going to have a 9 minus x to the negative 1/2 power. And we're going to have that in minus 1. Of course, we need to square the bottom as well. So the 2 becomes a 4. And the 9 minus x square rooted becomes just a 9 minus x. Now let's simplify this, because it looks like kind of a mess, doesn't it? First things first, I'm going to multiply the top and bottom by the square root of 9 minus x. What that's going to do, first of all, it's going to change this square root of 9 minus x. Because I'm multiplying it by itself, I'm just going to turn that into 9 minus x. Then over here, actually I can go ahead and cancel those out. We don't need those anymore. But when I multiply by the square root of 9 minus x, I'm basically taking the square root of 9 minus x divided by the same thing. That part's actually going to cancel out. So actually, I'm just going to skip right to the -1. So the top has already become a lot simpler. Unfortunately, the bottom doesn't become simpler. It actually gets a little bit more complicated. But it's not so much more complicated that that's too big of a problem. Basically, I have 9 minus x to the first power, and I'm going to multiply it by 9 minus x to the 1/2 power. If I combine 1 and 1/2, I get a new power of 3/2, which isn't too bad. Compared to what kind of mess we had on top before, this is a lot nicer. Now we do have some like terms. Basically here we had a -6 in front of this. We go ahead and distribute that. Here we actually cancel out the minus sign here with this minus sign here. Combine a bunch of like terms. I'm going to leave that to you guys to work out. Turns out what we get is 3x minus 36 with the same denominator. So, a lot simpler than what it could have been. But that is our second derivative. Alright, so we don't have to go back and look at our actual derivations anymore. All we need to have is our formulas. And we're going to go ahead and make use of these formulas to solve the questions. Our questions being, where are the relative extrema, what are they, and are there any points of inflection? So first things first, if we're trying to find any extrema points, all we need to do is first, where is this first derivative equal to 0, and where is it not exist? Well, if the first derivative equals 0, since we have a fraction here, that means the numerator has to equal 0. It means that 18 minus 3x has to equal 0. Of course, that means 3x has to equal 18, or that x equals 6. If we think about where the first derivative doesn't exist, well, it doesn't exist when there's a negative under the square root or when there's a 0 on the bottom. That happens whenever we're at 9 or larger. So basically, it doesn't exist at x is greater than or equal to 9, but since x is greater than 9 is not in the domain, remember our domain was only from -infinity to 9, we don't have to consider those at all, and we also don't consider critical points that end up at the endpoints of the domain. So actually, this is our only critical point. Now, we could make a number line for the first derivative, but since we already have the second derivative and we went through all that work to find the second derivative, let's make use of it. What is the second derivative at 6? Well, if I go ahead and plug that into my formula here, get 18 minus 36 over 4 times, 3 to the 3/2 power. Point here is this is approximately 0.87. And the main point here is that it is a negative number. Since we have a negative number for our second derivative at a point where the first derivative is equal to 0, we have a relative maximum at 6. That's what our second derivative tells us. We have a single critical point and it has a relative maximum at that critical point. Now, does this have any points of inflection? What are we talking about there? Well, we're talking about where is the second derivative equal to 0, or where does the second derivative not exist? Well, like the first derivative, the second derivative doesn't exist when x is 9 or bigger, and we kind of are already excluding that for the exact same reasons that we were for the first derivative. So, really we're asking, where is the second derivative equal to 0? Well, that's where the top is equal to 0. So 3x minus 36 equals 0, 3x equals 36, or x equals 12. Except 12 is not in our domain. Remember, our domain is only 9 and smaller. 12 is definitely not in that. So we can say right away that g does not have any inflection points. In fact, since we've already ruled out having any inflection points where the second derivative doesn't exist, then in fact, g has the same concavity for its entire domain, all the way from minus infinity to 9. And since we already actually identified that, we already saw that the second derivative is negative at 6, it has to be negative everywhere. So in fact, this whole thing is concave down. Let's go ahead and look at the graph of this just to kind of confirm what we got here. Remember, our function was just simply x times the square root of 9 minus x. Let's shrink the y values down a little bit. We have a point at 6 comma f of 6, and that is our relative maximum, like we identified. But we don't have any points of inflection. It doesn't actually ever change from being concave down. It's always opening downwards. And that's really all there is to it. Of course, we went through quite a bit of effort to find the derivatives. There's a lot of calculation involved here, kind of a lot of algebra, but the actual calculus involved here wasn't too bad. It was mostly algebra. Algebra is always the most fun part of calculus, isn't it? But here we now have some ideas of how it handle functions using their second derivatives. The second derivative is definitely a key point in actually doing stuff with functions, more than you might expect it to be. Though if you think about in terms of applications, the fact that we do when our functions represent, say, a distance, and we can talk about velocity and acceleration, acceleration being the second derivative, acceleration is an important concept. We really couldn't make do without that concept. And it's the exact same way with second derivatives in general. The second derivative does actually have enough of an impact on what the function looks like that it is worth talking about in a lot of cases. So we're not going to get to it right away, but later on in this chapter, we will make use of all these ideas that we've been going through, kind of put them all together, and actually just sit down with a function, identify all these pieces of information, and sketch that function by hand. And then we'll probably go ahead and use GeoGebra to check our work. But the point is, if we didn't have all this technology to do it for us, how would we do it ourselves? This is how we would do it. Alright, so I'll leave that for now. In our next section, we'll actually take a slight detour back to talking about extrema, but using the fact that we now have two different tests for extrema, the first derivative test and the second derivative test, and we'll apply those to various word problems. So meet me there, and we'll get into all that kind of fun stuff.